We are now in chapter 15, chemical equilibrium. And first we're going to discuss the concept of equilibrium. Why does this mean equilibrium? So equilibrium is a state where the concentrations, this is very important, concentration or molarity of reactants and products is constant with time. So if we look here, here we have concentration, here we have time. Notice the concentrations are not changing at this time. After this particular time right here, the concentrations of H2, NH3, and N2 are all constant. So we would say we are at equilibrium as soon as all the concentrations stop changing. Same thing here. We're at equilibrium right through here because the concentrations, the rate, actually. The rates, this is a different type of curve. Rates versus time. The rates are constant, therefore we are at equilibrium. And the forward rate and the reverse rate, notice they are equal. This is always true at equilibrium. The forward and reverse rate are equal. We learned that in kinetics. Okay, now one of the more important things about equilibrium is that even though the concentrations are constant right here, the reaction is still occurring. There's frantic or frenetic crazy activity, lots of activity going on. We are not in a static situation. It's a very dynamic situation. The reaction continues to occur. However, the concentrations themselves stay constant because the forward reaction and the reverse reaction are occurring at the same exact rate. All right. Now, this is just a random reaction. A, B, C, and D are the reactants and products. They can be gaseous or aqueous. And K is our equilibrium constant. This whole piece right here is called the equilibrium expression. Now, in order to identify the equilibrium expression, hang on, let's do it this way. We will cover what I don't want you to see yet. The equilibrium expression it's very easy. You take the product and you raise them to the power of their coefficients. So notice C would be raised to the L power, D would be raised to the M power right here. And we have products divided by reactants. So K is always products over reactants. And you raise each chemical to the power of its coefficient. So A to the J, B to the K. Right here. We'll learn later, this says A, B, C, and D are gaseous or aqueous substances. We'll learn a little later, if you have a solid or a liquid in your reaction, you do not include those in the equilibrium constant expression. Okay, very similarly to kinetics, the only thing that affects K, the equilibrium constant, is temperature. Nothing else changes K. If we change reactant or product concentrations, that does not affect K. If we change the concentrations of the products or the reactants, that will just change our final equilibrium conditions. The reaction will proceed to get back to equilibrium if we change any of the concentrations of the products or reactants. And the reaction proceeds to get back to the equilibrium state. So temperature, really important right here, temperature, the only thing that affects the equilibrium constant is temperature. So let's see how this connects to kinetics. So last chapter, we had a reversible reaction. When we were doing mechanisms, we learned that at equilibrium, K forward times the reactants raised to their powers is equal to K reverse, Kr, times the product chemicals raised to their power. Now if we isolate this to get Kf over Kr, we just pull Kr over to the left, we pull AB squared over to the right, we get this expression right here, and you should notice this looks just like K. We have products over reactants. So the equilibrium expression for this reaction right here would be AB2 over A times B squared, and that's K. So it turns out K is just Kf over Kr. We're not going to do any calculations with that, but I just want to give you an idea of physically what is K. It's a ratio of the rate constants of a forward and a reverse reaction. All right, now because of the definition of K, remember K is products over reactants. If K is really big, that means products over reactants is really big, which means products are really big compared to reactants, which would mean the right side, the products, are much larger than the reactants. We say equilibrium lies to the right, or we would say equilibrium favors the products. And if K is tiny, really, really small, remember K is products over reactants. So if products over reactants is tiny, that means products are small, reactants are big. The equilibrium lies to the left, and the reaction favors the reactants if K is very small. All right, so let's do an actual problem. So we have this situation where you're given a reaction and you're given you're given equilibrium concentrations of all of these chemicals, and you are asked to calculate K. So you're going to start working on this on your own. So K, I'll talk you through it. K will be products, NH3 squared, divided by reactants, H2 cubed times N2. And then you just plug in the numbers right here. So you might want to pause and fill that in. I'm going to show this to you. Okay. So again, pause it if you need to. So the equilibrium expression K is products over reactants, and you raise everything to the power of their coefficient. We just plug in the values since we were given actual equilibrium concentrations. So given equilibrium, Control Z. Given the equilibrium concentrations, we just plug those right into our equilibrium expression, solve, and we get a number. Simple, simple. Okay, next problem. Notice here we have reversed the reaction. It's the same temperature, and we have the same exact concentrations. So now I want you to solve for K for this reaction, and we would end up with exactly the same concentration. So use these concentrations from part A because the temperature is the same. The equilibrium concentrations are the same. Find K for this reaction right here. So you can pause, or I'm going to show you the solution right now. So pause. Okay. Equilibrium expression. We change where the products and reactants are. So now, since I reversed the reaction, the products are now defined as N2 times H2 cubed over the reactants, NH3 squared because of the 2 here. Just plug in the values that were given to you right up here. We saw that we get this number. Now you should notice right here, all I did, if you look at this expression here and this expression here, you should see that they are the reciprocals of one another. If we reverse a reaction, the K, this new K, is just 1 over the original K. So if you check on your mathematically, this number here is equal to the reciprocal of 3.8 times 10 to the minus 4. And I've just summarized what I said right there. Okay, so we have some generalizations for equilibrium constants. First, what we just learned, if you reverse a reaction, the equilibrium constant is the reciprocal of the original equilibrium constant. If you multiply a reaction by a number or a factor n, then you raise the equilibrium constant to that power n. Okay? Kind of like Hess's law, but Hess's law was all addition, subtraction, so we just added the different delta H's. With equilibrium constants, because equilibrium is all multiplication and division, we now have to raise to a power rather than adding or subtracting. K has no units. We don't worry about units of K, and we mentioned this earlier. If K is very small, the reactants are favored. If K is very large, the products are favored. Okay, so we've been talking just about concentrations. So far I gave you molarity for the problem that we did. And sometimes we deal with partial pressures instead of molarity. When you see just the letter K with nothing else on it, we're talking about concentrations. But now we're going to get into a new kind of K, something called a Kp. So the K we were doing before is called a Kc, C for concentration, where we just use concentrations. Kp, same exact idea, but we're using partial pressures. So if you see this little p here, we're talking about an equilibrium constant based on partial pressures. P is for pressure. Okay, and we have a relationship between Kp and Kc. They are mathematically connected to each other through the ideal gas law. Here's your equation right here, and here's your definition. So Kp is just the original K we were working with times RT raised to the delta N, where delta N is the moles of gaseous products minus the moles of gaseous reactants. And you have to make sure you use the right R. That's the 0.0821 atmospheres liters per mole Kelvin. Let's do a quick problem for this. So find Kp for question 1A on page 2. Here's question 1A on page 2. So we found here that this was the Kc, and we want to find Kp. Now again, you can pause this, do it yourself if you want. I'm going to talk you through it. Remember, Kp is Kc times RT to the delta N, so we have to look at delta N here. And we have 2 moles of product gases. We only look at the gases. It's all gases. We have 3 plus 1 is 4 moles of gaseous reactant. So there's our reaction. We were given the Kc. Delta N is 2 minus 4. We just plug into the equation. You can pause if you want to do this on your own. Plug that into our equation. Oh, very important. Kelvin. Temperature is in Kelvin. Really important. And you should be getting Kp is 35. Okay, heterogeneous equilibria. That just means we have more than one phase present. Remember, homogeneous mixtures, heterogeneous mixtures. We see these words hetero and homogeneous all over the place. So if we have more than one phase, equilibrium is heterogeneous. I mentioned this earlier. When we have heterogeneous equilibria, we just ignore the liquids and the solids in the equilibrium expression because their concentrations are constant. So equilibrium is not dependent on a solid or a liquid concentration because those are constant, and we don't include solids and liquids in the equilibrium expressions. It's just important when you're writing an expression, leave out the solids and liquids. Okay, what does equilibrium constant tell us? We can determine if a reaction will move left or right based on, I'm not sure what I was just saying because, go ahead.
Hi everyone, I'm Chris.
Chris just walked in and caught me mid-sentence. So anyway, bye Chris. Let's see, where were we? What does equilibrium constant tell us? Oh, it tells us if a reaction will move to the left or right toward the products or the reactants. And to figure this out, we look at something called Q, the reaction quotient. Q is exactly the same as K in terms of the form of it, but we use initial concentrations instead of equilibrium concentrations. This confuses students often. You have to just remember, for Q, it's initial concentrations, not equilibrium. Equilibrium is K, Q is initial. It's called the reaction quotient. Q is for quotient. And we have 3 possibilities. We could end up with Q equaling K. That just means we're at equilibrium. If Q is bigger than K, let me move this down. We don't need to have that looking funny there. Okay, if Q is bigger than K, it's important to remember that Q and K are both products over reactants. So if Q, grab my microphone here. If Q is bigger than K, that means Q bigger than K right here. That means this is too big. That's too big. Q is too big. We need to get smaller, which means we need products to go down, which means we will go toward the reactants, and we will shift left toward the reactants. Okay. Now this next example, Q is less than K. Okay, so products over reactants. This is less than K. Q is product over reactants. It's less than K. And we always, at equilibrium, we have to get back to K. We got to be at K. So if this piece is too small, that means we need the numerator to get bigger, right? Because we got to get a bigger number. We need products to go up in order to get back to K. We're always trying to get to equilibrium. So initially, products are too small. They need to go up if Q is less than K. And the reaction will shift to the right. Okay, so we're going to do a problem. Again, working with our equilibrium expression. We're synthesizing ammonia. We have the reaction written somewhere else. Hang on a second. That reaction was over here on, I don't know, it's the second or third page. So this is the reaction we're working with. It's very important that you need your reaction in order to figure out your Ks. So that's our reaction we're working with. We're going to plug in the initial concentrations into this expression right here. That will give us Q. So we'll have NH3 squared over H2 cubed times N2, and you can solve for Q if you can pause this if you'd like, or I'm going to show you the solution right now. So we just plug in our values, and we get Q, and we see this Q right here is much bigger than K. So Q is too big. That means the products are too big, which means we need to go left. So we will go toward the reactions. We will shift toward the reactants. Okay, important note. When we shift left, that does not mean that the products are now reactants. The way you write the reaction down defines products and reactants. So when we reverse a reaction, we are not suddenly saying that the reactants are products and the products are reactants. We're just saying we're shifting left. Reactants are defined as being on the left, products as being defined as whatever is on the right. Okay, here are two more problems. Same reaction, same question. Determine if the reaction will shift to the left or to the right, or not shift at all. And pause this, work out the problems, and I'm about to show you the answers. There's your answers. Okay, these two, they're close enough. We're at equilibrium. Here, Q, 0.002, is smaller than 0.006, so Q is less than K. Reaction shifts right. Okay, so new problem. Just going to use all the concepts we've learned, put it all together. We have a reaction, and if you want to pause this, do it on your own, you are welcome to do that. We're given the Kp. We are given the equilibrium, not initial, but equilibrium pressure of N2O4, and we're asked to solve for the pressure of NO2. So, again, you can pause if you know how to do this. We'll just write the equilibrium expression. Kp will be NO2 squared over N2O4. Plug in our values for the Kp and the N2O4 and solve for the missing. So here's your solution. There's our Kp expression. Plug in the numbers. I plugged in this number here and moved it over to the other side to get 0.133 times 0.2.71. Took the square root because this was squared, and we get our answer. All right, now, ice boxes. Initial, change, equilibrium. Sometimes in problems, we are given initial and equilibrium information. When this happens, we create ice boxes. So here's some key words. This evacuated container is filled with nitrogen and hydrogen. So this is an initial condition. This is also an initial condition. And then we are told at equilibrium we have this. We write our reaction, N2 plus 3H2. These are all gases, so there's nothing we're not including. We have our initial conditions. So I for initial, ice, initial change equilibrium. Initially, what do we know? N2 is 0.50, H2 is 1.0, and this was an evacuated container. We did not put any ammonia in there, so the ammonia is initially 0. Now the change. This is the confusing part. First off, reaction, does it go left or right? We don't have any product to react. It has to go to the right. If we had some product to react, we would have to calculate Q. Remember earlier, calculate Q and figure out which way the reaction goes. So we know reaction goes right. This has to go down. Hydrogen has to go down. N2 has to go up. Now, you use the coefficients, the numbers in front here, and that's what we do in the change column. So we first figure out whether it's plus or minus, and then we figure out what numbers, how many x. We don't know what x is, but if N2 goes down by x, we know that H2 right here has to go up, down by 3x, because there's a 1 to 3 ratio between the N2 and H2. And then the NH3, there's a 2 here. So for every 1 N2 that reacts, 2 NH3s are formed. So we have 2x over here. Now we have E for equilibrium. E is just equal to I plus C. So we have 0.5 minus x. I'm just adding the first two rows together. I have 1 minus 3x. Let's put a little line here so we can see everything more clearly. And this is 2x. Okay. Now we have our icebox, and then we'll have our little given. If there's anything that's given to us at equilibrium, not initial, but equilibrium. Oh, look, right here we have it. At equilibrium, NH3 is 0.10. So at equilibrium, NH3 is 0.10. So I know that 2x is equal to 1.0. X is, 0.10. 0.10. X is 0.05. Now I can solve for everything. So I have x is 0.05, so I have 1 minus 3 times 0.05. And I have 0.5 minus 0.05. Let's get rid of this. And this is equal to 0.45. This is equal to 0.85. And this is 0.10. Now let's see, what were we asked for? Find the equilibrium concentration of all species. So we now know N2 is 0.45 molar. H2 is 0.85 molar. And we were already given the NH3, so we don't need to write that down as an answer. But you have to make sure you don't only fill in an icebox, you have to actually write out your answer. And we were also asked for what's the equilibrium constant at the temperature of this reaction. And K, the equilibrium constant, is just products of the reactants, so it's NH3 squared over N2 times H2 cubed. Plug in our values, and there we go. We get K is 0.036. I just plugged the values, the equilibrium values, into our equilibrium expression. Solve for K. Okay, we got 2 more problems to go. Problem 6, important pieces here, certain temperature. Make sure when you do equilibrium, we always have to do concentration. So if we're given moles and liters, we have to calculate molarity, but it's easy, it's 1 liter, so moles and molarity are the same. But here we have initial conditions right here. And then over here, we have equilibrium conditions. So I need an icebox because I've got initial and equilibrium. Now you can pause this, do it yourself. I'm about to show you the entire solution. So initial conditions right here, equilibrium, you put in all the givens. We have minus x plus x. Because it's 1, 1, 1, and the reaction has to go to the right because there's no Cl2 there, so we can't go left. Reaction has to go right. We know x is 0.002. We plug that in, solve for K, and we have our final concentrations as well as K. Okay, and the last problem, there's a trick to this problem. There's a square root trick. So if you want to pause this, do it on your own. You'll get to a point where you'll find you aren't given anything at equilibrium, so how do you solve this? So here's a reaction. You're given the equilibrium constant. and you want to find all the equilibrium concentrations. You're given initial information. So here's our initial information. And you have to calculate Q to figure out which way the reaction is going to go. And Q is just 1 times 1 over 1 times 1, which is 1. 1 is less than 5. That means Q is too small, which means we need more products, so we're going to go to the right. Okay, so minus x plus x plus x, because all the coefficients are 1. If there had been a different coefficient here, we would just put that number in front of the x. Okay, we add the initial plus the change to get the equilibrium. I plus c equals e. And then when we do this K equation, here's the trick right here. Notice we plug everything in. Do you notice you have 1 plus x squared over 1 minus x squared? You do not want to solve a quadratic. That is complicated. What you do is you take the square root of both sides. And this simplifies into, we take the square root of both sides, simplifies into 1 plus x over 1 minus x is the square root of 5.1. And now that's easy. This is just algebra. And we get our answers right here. We solve for x, and the CO2 and the H2 concentrations are 1 plus x. The CO and H2O are the 1 minus x right there. And that's it.